Flavio asked how I'd go about attracting a piece of vellum towards the geometry, towards the surface, and I thought it would make for a nice quick tip, so here we go, here's what I do. So the theory behind this is really straightforward. What we want to do is wrap this piece of cloth here around the geo, in this case, this cube, for example. And the first thing we do is, for each point on our cloth, we find the closest point to it on our geometry, in this case our cube. For example, this point. So that's the closest point to this point here. Next, we'll calculate the vector pointing from this point on our cloth to the point on the geo by just subtracting the point's positions. However, if we just use this vector as our force, we'd run into trouble. As the cloth would be attracted closer and closer to the cube, the vector and the resulting force would get smaller. And to counteract or to prevent this, what we do is we will normalize this vector pointing from a point to the cube. And what that means is we will just scale this vector so it has a length of 1. And what we finally can do is scale the resulting vector by some factor, and thus scaling the resulting force, which will pull the cloth to the cube, no matter how far away it is from the surface of the cube. So let's build this in Houdini. Start out with a grid, that will be my piece of cloth, dive in there, scale it back to say 3 by 3, and give it maybe 40 by 40 rows and columns like this, then move it up. Say 1 unit like that. And also I'm going to build a collider. Torus works fine for me, whatever surface you like. And then maybe scale this down a bit in diameter, like so, and increase the rows and columns here as well, like this. Maybe decrease the radius, like that. Then drop down a vellum configure cloth to turn my grid into a cloth, and also wire in the collider here, and maybe attach a null, call this one out underscore collider. Like this. And then after the vellum cloth here, let's just append our vellum solver like that, increase our substeps to 2, the constraint iterations maybe to 20, highlight it, and then sim it for the first time. So that's totally behaving as we'd expect. Cloth is flapping down here. Let's disable the grid in the viewport, and let's attract this cloth to this torus actually. By first, just so you can see what it's doing actually, I want to disable gravity, set this to 0, and then resim. So we don't see nothing. This is just not falling down onto this torus here, as we don't have any gravity. So let's instead create a custom force by diving into our vellum solver, and in here attach a pop wrangle to our force output. And that's how I can actually vex my forces or my velocities, or basically any points on my simulated surface. However, before I start writing any expression in here, I'd like to set up my inputs correctly. So input 1, I'll leave that as the default none, so I'll work on the pop stream actually in here. And input 2 will point to a SOP. In this case, the out collider, the out underscore collider. I could also set this to the third context geometry in this case, but let's leave it set like that. So what I want to do for each of those points that make up my grid is I want to search the closest point towards any point on that grid on the torus, and then attract my point towards the closest point on the torus. Let's do that by creating an integer, which will store the point number of my closest points, call this npt, and let's use the near point function. I'm going to search on my input that I set up here on input number 2, the SOP, which I'll access by its ID 1. And I will look from my current point position on the grid, v at p, like that. Next, I need to get this closest point's position actually. So I'm going to get that by declaring a vector, call it npos, and use the point function to access the position attribute of our point on the torus. So slot with the ID 1, attribute name p, and npt is the point's number, like this. Now let's calculate that vector pointing from the grid to that point on the torus. Call it f, short for force, and it should be equal to our newest position minus our particle's position. However, if I feed this vector now directly into our force, what will happen is the force will get smaller the closer our grid gets towards the torus. So instead, because the distance from the grid to the torus gets smaller, and so this whole vector that we're calculating here gets smaller. So to prevent that, let's normalize this. So basically scale our vector to a length of 1. And then multiply it with an amplitude, just with a scaling factor, to give it a constant scale of, say, maybe 0.4. So what this line does is, first, we calculate this difference, spitting out this vector pointing from the grid to that closest point on the torus. Then I normalize this, so I scale this vector, the result of this calculation, to a vector of a length 1, and then again multiply this, so it's now a vector of length 0.4. And now finally, let's write this onto our force vector, v at force equals to f, like this. let's keep our fingers crossed and hit play. We can see this is now attracted to the torus's surface and wraps around the torus neatly. With this amplitude scaling factor here, I can adjust the strength of this behavior of the force. But that's about it. So now you have some neat torus or object wrapper, I guess. So I'm kind of intrigued to see what you guys come up with here and what stuff you're going to wrap with this. Please don't make it as weird as usual, but yeah, do whatever you like. So really quick one today. Again, I'm intrigued to see what you produce using this. And until next week, it's cheers and goodbye.